So I want to talk today about a method to shape electron beams using membranes, very thin membranes that we can engineer by nanofabrication. And I'll also discuss some applications of this method. So in fact, you can already see maybe the highlight of what I'm going to discuss. So this is an electron beam and a lens. And usually, as we heard also from Lotan, this lens has a spherical aberration. So one application that I'm going to show is that we can add some very thin membrane just before this lens, and this will just cancel the spherical aberration of the lens, and then we can get better, we can have better resolution with the microscope by just adding this membrane. So I guess I don't have to say too much about transmission electron microscope in this audience, this picture of one of them, but let me just say that what do we have inside this column? So essentially we have an electron gun, and then we have a magnet or several lenses that are actually coiled magnets that focus the beam onto a sample. And then we have some additional lenses for projection and magnification. So this is what you have essentially in all the transmission electron microscopes. And the key element here is this lens. So this is maybe a cartoon of it, and this is a picture of how it looks like. So this is what is called the pole piece lens. So what we have is we have here a coil where current is applied. And this current causes this electron beam to focus. This is the way essentially all the electron microscopes work. And the problem, as we also heard earlier from Lothar, and this is something that is known already from 1936, is that this lens has an inherent spherical aberration. I want to emphasize this is a technical problem that I can design some different shape of a pole piece. This is a fundamental problem that we have with rotational symmetric lens. And the effect of spherical aberration is the following, that if this is what we would like to have, we have a perfect lens, we would like to have all the rays to focus on the focal plane. But when we have spherical aberrations, depending on how far we are from the optical axis, the focal length changes. So these rays that are further apart focus at a shorter focal length. So therefore, we have some blur. This is not on the geometric sense, this is not a perfect point. There is some aberration because of this problem. And in other areas, like for example, in light optics, this can be solved very easily. I can just add another element that will just do the opposite. We'll add just the opposite aberration. And then I can fix the spherical aberration. But this is not so simple in electron microscope. For example, we don't know how to make a negative magnetic lens, which is what is needed if we want to implement this idea. So in fact, although this problem is known from 1936, it took almost 63 or 64 years until a solution to this problem was found. And the solution is what is called multiple correctors. So the idea is that if the problem comes from rotational symmetry, we will break this rotational symmetry. So we will add elements which consist of a series of magnetic tips. Each one is driven by its own coil. I can have different current to each one. And you see, this is no longer rotational symmetry. And this was done independently, both by a group in Germany, Heider, Rosen, Urban, that won the Wolf Prize for that, and also by Krivanek. And as we also heard, this year, all these inventors got the Kavli Prize, because this is considered a very important discovery that enables the electron microscope to reach atomic scale resolution. Now, how does it look like? So this is these are pictures of a Titan microscope. And here we have two examples of these correctors. This is a probe corrector. So the sample is here. This is where the sample is here. So this is the corrector. And so this corrects the probe in a scanning transmission electron microscope. Or we can have the corrector after the sample. Again, now the sample is here, and this is the corrector. And this is what we have in a transmission electron microscope. So this corrects the image. So one thing you can already see is that this is a very large and bulky element. And moreover, let's say you have an existing microscope, you can not just open it and insert this element. Essentially, what you have to do is you should throw away your existing microscope, buy a new one, which is aberration corrected. And so these are the limitations. It's very costly, usually doubles the price of the microscope. It's very large. You cannot upgrade an existing microscope. And finally, this I will get towards the end of the talk. It doesn't work for all the lenses that you have. Let's say even you already put 3 or 4 million euros and you bought a transmission electron microscope. So the corrector works for a specific lens, for the objective lens. If you want to work with some other mode, that for example use the condenser lens, you will find out that even now in this aberration corrected microscope, you cannot use the corrector because it's not suitable for this lens. And for example, if you want to study magnetic materials, this could be a limitation. So what I want to show is that there is another alternative, which is just to take the existing column that I showed before and insert into an existing aperture without any other modification, a very thin membrane, a phase mask that will correct the aberrations. But before I'll get to that, let me tell you a little bit about the technology of shaping electron beams in general using sculpted membranes. So essentially what we are using is the silicon nitride membranes, which are also used for, they were mentioned here in some of the other talks. They are usually used to hold the samples, but we are using the membrane itself as a mask in order to shape the electron beam. And there are two methods that I will show you. One is to make this mask into an amplitude mask, and the other one is to make it a phase mask. And the shaping itself is done by nanotechnology fabrication tools. We use a focused ion beam to achieve this shaping. So here I show you how to make an amplitude mask. So essentially, this is the same membrane that, or part of it that I showed you before. What we can do is we can coat it with some layer of metal that makes it opaque. And then we can define some openings, again, using feed. So essentially, where we removed the metal, the electron beam can pass. And this is how we modulate the wavefront of the electron beam. And this is a very simple method. It's very reliable. It has some difficulties, but I will discuss that in a minute. But there is another way. The other way is to use the membrane itself and change the thickness of the membrane, because once we pass through this membrane, we accumulate a phase shift that depends on the thickness of the membrane. So if we change the membrane thickness, we can actually achieve a phase mask. And these are some examples. I will show them in 1 or 2 slides later. So in fact, what gave us and others the motivation to this is these works by Verbeek and McMorran about 10 years ago, where they showed how to generate vortex beams using these amplitude masks. So here is just an electron beam, and this mask converts it into a beam that is split into multiple orders. And because this is this has a fork shape, what we get here, let's say in the first order, is a vortex beam. This is also a vortex beam. with an opposite state charge and so on. And our own first contribution to it was to use the same concept in order to generate Airy beams using electron beams. So I want to emphasize that this is a very versatile tool to shape electron beams done by my former student Roy Shilo, which is I want to shape a beam so that the intensity pattern will follow this shape, which is called an Archimedes spiral. Okay, so this is defined here. These are the X, Y, and Z coordinate of this Archimedes spiral. And essentially we can design it and we can fabricate. This is how this mask look like. So we essentially have some holes that where the electron can pass. And if we design it correctly, then in the first diffraction order, we will see this Archimedes spiral. This is an on-off and off-axis hologram. So this is what we see in different. We can look at different z-planes, and this is simulation and measurements, and you can see that this beam follows this Archimedes spiral trajectory. I can also show you this in a movie. So what you will see here, what you see is now the expanded zero order, which is not so interesting. You will see the +1 and -1 orders. And what I'm when I run the movie, you will see images of different z-planes. So let's do it. And now if you look here, you will see, yeah, here you see this Archimedes spiral, both for the +1 and for the -1 order. So you can see this is a very versatile tool. You can do a very nice thing with it. This still works. This is an amplitude mask, so it has some disadvantages. You have orders, as you just saw, and you have losses because of it's an amplitude mask. So there is a better way, perhaps, is to make a phase mask. So as I said, the silicon nitride membrane itself is a phase element, and we can calculate what is the phase accumulation of the thickness. In fact, there is an equation here. It depends on only two parameters. Well, it depends on the thickness, but other than that, it depends on the electron energy and on a material property, which is the mean inner potential. So if we work with silicon nitride, which is shown here, and we work with 200 kilovolts, so we can see that about 40 or 45 nanometers membrane is enough to accumulate a phase shift of pi. This means that we don't need a very thick hologram. Very thin hologram, less than 100 nanometers, can give us 2 pi phase shift. And with 2 pi phase shift, we can do everything with a phase mask. So these are just examples of using now phase masks to generate beams. So this is a phase grating. This is a mask that generates Hermite-Gauss 1-1 beam. So we have here 4 quadrants. In 2 of them, we have a phase difference of pi. These are milled to about 45 nanometers with respect to these 2. So they generate this 4-lobe electron beam. Or we can make this a spiral phase mask, and this generates a vortex beam. But of course, we are not limited only to this very versatile. So these are some more sophisticated shapes and more sophisticated masks, which were designed by Gershberg-Saxton algorithm. So here, this is a mask that generates electron beam with the initials of Tel Aviv University. I want to emphasize, we are not scanning. This is the shape of the electron beam itself, okay? It's, Tel Aviv University, or another one which is the shape of the believed shape of the atom, where actually this is the zero order. So the mask you can see here. Essentially, we go point by. So these are like the pixels of this phase mask. And if we do it correctly, then we can get the shape that we want. Okay, so now let's get back to aberration correction. So in fact, the idea is already clear. We know that the lens, the magnetic lens, is inducing aberrations. So what we want to do is we want to design and fabricate a phase mask. We are going to insert it into an existing aperture microscope. We don't need any modifications. It's something that is available. And this phase mask should just cancel the aberration of the objective lens. Now, I should say we are not the first to think about it. You can see some previous attempts by Boresh and Wilash and Ito over the years. And in fact, all of them failed. And I think they failed because the technology, meaning nanofabrication technology, was not available at that time. So before going to spherical aberration, we just wanted to see that we can do other kinds of aberrations. So these are two examples of aberrations that we can use. What we do here, we show that we can add aberration. Of course, if we can add aberration, it means that we can correct aberration, because if we just add the aberrations that the lens has, but with the opposite sign, then we cancel it. But just to first to understand, here we add astigmatism. So this is the way the mask looks like. And these, the colored ones are simulation, and these are measurements of how the beam looks like at the different z-planes. And this is the, and this is a trefoil aberration, okay? So, and later we can do also, we also added the spherical aberration. So again, you can see, again, these are simulations and measurements of how the beam would look like at different z-planes. So far what we did is we added aberrations. What we want to do next is to, we want to correct aberrations. So here we have to be very specific and very accurate and add exactly the right amount of aberration for the lens that we work with. Let me first maybe go over this slide, this figure that explains what are the trade-offs. So what we see is what is the probe side as a function of the numerical aperture. So if we have only diffraction, then as the numerical aperture increases, the probe size will just go down. Whereas if we have spherical aberrations, as the numerical aperture increases, the probe size will go up. So there is some balance between them. There is some optimal point. In the microscope we work with, this is around 180 picometer. But, and what we want to do now is we want to correct the spherical aberration. So let's say we correct it for this point. So now we go from this point, which is around 180 picometer, to about 100 picometer, a little bit more than that. And to achieve this, this is the way the corrector should look like. And this is a fabricated corrector. So here we can see, this is a microscope picture. So in fact, we can have several correctors, even with slightly different design on the same membrane. And here you can see a microscope, a TEM image of it. Why this is a bit darker here than here? Because it's thicker in the middle than in the sides. And again, it becomes thicker here. So this is why the edge and the middle is a bit darker than this range. And from this, we can also fit and see that what we fabricated is what we planned for. And now this is already a scanning of a silicon sample. So on the left, what we see is the silicon picture without the corrector. And in fact, you see that this looks like an ellipse and not like a circle. Why? Because there are actually two silicon atoms which are very close onto the other. This is the silicon dumbbell that you cannot resolve without the correction. Once we add the corrector, you see these are resolved. This is also seen in the diffraction plane. In fact, these two atoms are 160 picometer apart. So once we do it, we can resolve this point that was not resolved otherwise. And this was also made for another sample where the distance was a bit smaller, about 128 picometer. Also here we could resolve with the corrector. As I said, without the corrector, the resolution was about 180 picometer. So there are different ways to assess the correction. Maybe the most quantitative one is by making a ronchigram measurement, where we focus the beam onto an amorphous sample. In this case, we use an amorphous carbon. And then we can measure the angle of where the image looks, let's say, kind of homogeneous. So without the corrector, this angle is 7.4 milliradian. This is in fact, the angle where you have still, you're still not limited by spherical aberration. But once we add our corrector, this angle goes up to 12 milliradians. This is why we have better resolution. We can also image the probe size because the microscope we worked with was image corrected. It was not probe corrected, but it was image corrected. So we can see that the image itself becomes smaller from 180 to 124. And we can also look at it using simulations. This is again simulation of these silicon dumbbells, which is not resolved with this spot, but it is resolved with this spot. Finally, we can also use the same sample and check how it will look like with the regular commercial multiple correctors. So of course, obviously in both of them you can resolve the silicon dumbbells. In the multiple corrector, the image is sharper or stronger, let's say. Why? Because what we do is we physically insert a membrane. So we have some scattering, we have some loss of signal. And this is maybe a limitation of our method. I will discuss, or I should say this membrane that we use is relatively thick. It's a 200 nanometer membrane. I'll show you in a minute a thinner membrane where the scattering is less than that. Okay, so finally I come to the last topic, which is ongoing work on how to use this technology for studying of magnetic materials. So one way to study magnetic materials is what is called Lorentz. So idea is the following. I have here some magnetic material. I cannot use the objective lens because then the residual magnetic field from the lens will damage my measurement. So I have to switch it off. But then I can use a condenser lens, which has a much larger distance. Because of the larger distance, I'm not worried about the residual magnetic field from the condenser lens. And once the electron beam goes to a magnetic material, it will deflect depending on the orientation and the strength of the magnetization. So this is Lorentz STEM. The problem is if I want to have good resolution, I need to correct the aberration of this condenser lens. Now, the thing is, even if you have an aberration-corrected microscope, at least from FEI, which is the largest manufacturer, you cannot correct this, the aberrations of this lens. So what we suggest is to, in fact, to do the same technique that I showed you before, but now to apply it to this lens. So this will open the ability to do Lorentz STEM with much higher resolution. And essentially, we believe that we can approach the 1 nanometer resolution using this method. This is some very preliminary result done by Dolev Reutemann and Penghan Lu. So this is the corrector. It's a much larger corrector, 150 micron. This is the F10 thickness measurement. And again, this is a ronchigram, so we can see that at a certain angle of 1.3 milliradian, we corrected the spherical aberration. And now we can, in this measurement, we can compare an uncorrected and corrected scan, and you can see some details that appear in the corrected measurement. For example, this granularity that you see if you use the corrected mask is washed out without it. And this is still a very preliminary measurement, but it shows that we actually can already improve the resolution of the condenser lens. So to summarize, I hope I convince you that it's now possible to arbitrarily shape electron beams using masks, both amplitude mask and phase mask, and you can shape the beam both in 2D and in 3D. And I talked mainly about one application, which is aberration corrector. This can be used in existing electron microscope. You don't need to buy a new microscope if you want to improve your resolution. We already showed resolution improvement in one specific microscope. We think that the potential is to reach below 1 angstrom. And finally, I'll talk also about another option that can be used with these technologies to do correction of the condenser lens for Lorentz STEM microscopy, which may enable to study magnetic materials with a resolution of about 1 nanometer. And before I end, let me thank my students and my collaborators. So 3 former students, Roy Shilo, Roy Remes, and Noah Wolach-Bloch, worked on it, and now this is continuing by the Lev Reutemann. I worked with colleagues in Tel Aviv University, Professor Avi Gover, Dr. Yossi Larea, and Dr. Yigali Lach, and also with colleagues from Jülich in Germany, Peng and Lu, Amir Tavabi, and Professor Rafael Donin-Gorkowski. Thank you very much.
Okay, thank you very much for a nice talk and an original approach to how to correct aberrations. I have here one question from the audience. It's Kristina Bukvishova. She asked, what about the lifetime of membranes? Isn't there some contamination and so on?
Okay, thank you. It's a very good talk, very good question. So at least for the membrane that we use for aberration correction of the Titan roller, the one that I showed before, we have a record of about 7 months that we worked with, and we didn't see any degradation. So I should explain also why we don't see degradation. And the reason is that because we work, maybe I can show it. So we work here where the electron beam is very large, it's about 50 microns. If I would put the corrector here where the electron beam would be, I don't know, 1 nanometer, then the dose will be very high. But here, the dose is very low. So in fact, at least this is our experience, that we worked for quite a long time with the same mask and we didn't see any degradation.
Okay, is there any other question?
Gilad has a question.
Yeah, Adi, that was very nice. Thank you. So in biological cryo-EM, people use a phase plate in order to generate phase contrast and actually see those very low density samples in ice. Can you combine that with your aberration correction and do both activities in the same phase plate, basically?
Yeah, so the phase plate, this is like in Zernike mode. So it's actually is put after the lens. It's put in the diffraction plane usually. I think this could be used, so this is not where we are using it now. Now we are correcting the problem. It could be used, for example, to do image correction. You can, if you put the corrector after the sample, you can use it for image correction. And I don't know if this is an interesting question, if you can do at the same time both contrast enhancement and image correction. But I should say that for image correction, there are other challenges. There are off-axis aberrations that you have to deal with. When you do, when you work in STEM, in scanning TEM, you are always on axis with the beam. Only after it passes the sample, you have beams that go in different directions. So this is much more challenging to do image correction, and also the dose is much higher. But yeah, I think it could be an interesting idea. We follow the work of on these plates for biological samples, and I think there are some interesting possibilities there. Yes, thank you.
Thank you.
Okay, that's a please short answer. What about dispersion? Is it depending on energy of electrons, the function of those elements?
Yes. So what we do here does not. It's correction for spherical aberration. So the chromatic aberration we don't deal with. I can show something that I skipped. It was fast, so maybe I didn't have time to mention it. This is in this measurement. This is the chromatic aberration. Okay, this gray line. So at least in this measurement, it's not. It's still not an issue. But maybe if we go to higher NA, or for example, in the Lorentz STEM mode, this becomes an issue. Then chromatic aberration is already something that we have to deal with.
Okay.